All right, in this video, we're going to keep on trucking with these equations that we saw in the last one. In the last video, we talked about efficiency. We talked about height equivalent to a theoretical plate, the variations that these equations are going to show up in. And the reason, one of the changes, is because we are looking at plates. We're not looking at columns. So these look a little different than before when we talked about general intro to chromatography. Resolution is also going to look a little different. Not quite, but you know, there's some small changes that are with these. And we can still talk about the resolution of two spots or two samples on a plate. So for instance, here is a lane that is a microscope plate, maybe is what I'm doing. And then here's my origin spot, and I see a spot here and I see a spot there. So the question is, what is the resolution of those two spots? If we go back to general intro to chromatography, we talked about separation. And in those terms, we talked about how the peaks are separated from each other. So for instance, baseline, 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 and I don't see anything, and then, oh, I see something, look at me, and then pew, pew, there it goes, and then here's another one, and then pew, pew, there it goes. So the distance here is that resolution when we get that equation and we plug those values into that equation. Does that number 1.5 or greater happen? Because that is our threshold of resolution. We've got really good separation if that goes on. So with resolution with a plate, it looks very similar. I'm going to take x's, and the x's are the spot differences. So the migration distance of this first spot and the migration distance of the second spot. That is what these x's are supposed to represent. And then here what we're doing, instead of width at the bases, we are doing width of the spots. If I go back and take a look at resolution for that intro to chroma, it was talking about width at the bases. Now, we do not have peaks, so we can't do bases here, but we can do width of the spots. That's okay. So that is this equation, W1 and W2. It is the width of the spot of the first one and a width of the spot at the second one. So I'm going to take those widths and I'm going to add them up. If they are larger blobby spots, those numbers are going to be bigger. And of course, that's going to play a role in if these spots are separated good enough or not. So with this type of equation, what I'm going to see is 2 times, and up on top is the migration distance for the first spot in centimeters. So let's say that was a 2.3. And then it is the migration distance of the second one. So let's say that is 4.1. Okay, great. There's your distance. There's your measurement. You did it in centimeters. That's not a problem. Now let's take a look at the width of the spots. That's also going to have to be done in centimeters. So let's say the first spot is 1 centimeter wide. That's fairly large, folks, if you look at a ruler for a spot. And then let's say that our other spot is 0.5. Okay, not a problem. So I'm going to take 2.3 and 4.1, add those up first, and get a number. Do not shortcut these steps. And then on the bottom, I'm going to take these two, and I'm going to add them up, and I'm going to get another number. Do not baby shortcut steps. And then I'm going to take those two numbers, I'm going to divide them. Do not baby shortcut steps. And then when I get that, I'm going to multiply by 2. When I do that, that will give me resolution. If that resolution is an acceptable amount, and again, we love 1.5 or greater, then this is great. The resolution is okay. That is not a problem at all. All right. All right, so there's 3 equations. They do represent a little bit about what we've already discussed. The concepts are the same at least. The equations look slightly different, but that's okay because most of the time on these tests that you're going to take with me anyway, I give you those equations. You just got to know what you got to plug where. There's no sense in memorizing those. Just know how to use them. That's what this is going to be all about. All right. Characteristics of TLC: absorption phenomenon of the stationary phase is substantially reduced once a large part of the absorption sites are occupied. Okay, so this is a concept that things slow down as we go up. We've talked about this before. That gas phase latches on to silica. The mobile phase latches on to silica. That silica is an interaction point. As those interaction points become limited, there are less and less spots for things to interact with. So I begin to see things slow down. I begin to see things travel through differently because of that. As the sign says on the screen, there is no vacancy at this Bates Motel. I am sorry, keep on going unless you want to see cray cray. If cray cray is up at the counter and you think cray cray's great and you like the way that cray cray looks, then maybe that's right up your alley. But I don't want cray cray to put on a wig and run around like his mama, and then while she's dead up on the second floor of the house that lives up on the hill. I don't want that kind of cray cray. But the vacancy is a thing. So vacancy has to be there in order for these compounds to interact with things and for them to slow down and actually begin to separate from each other. Okay. Next up, keep in mind, in order to get better spots, there's a couple of things that you've got to do. Number one, the speed is not consistent. That is okay. You got to accept that fact. Do not try to speed up the separation. Number two, taller plates do not give you better separation. We've already discussed this. Taller plates mean you develop longer. If you develop longer, things get fuzzier. Number three, saturated chambers are going to be preferred. So this is the concept. You let the gas phase fill up and you let the gas phase form first before you put the plate on the inside. It gives you more consistency, but it also gives you better spots that do not smear, that do not lag, that do not do any kind of crazy shapes. Next up, separation or stationary phase is very important. Maybe a silica, straight up silica is not appropriate for your method. Maybe you need to modify that in some form or fashion and do different types of plates. If so, that's okay. But your RFs for these spots, alert, alert, canvas, canvas, test, test, should be between 0.2 and 0.8. That is the ideal range for RF values. You don't really like to see anything below. You don't like to see anything above. Keep in mind, what was the UV absorbance rate, right? We're like, anytime you use the UV, you want an absorbance between 0.2 absorbance to 1. Definitely not anything 1.5 or higher. This kind of goes hand in hand with that, but it's really talking about migration rates. It's not talking about absorption here. The idea here is that on a plate, here's my start point. I want things to move. I want things to migrate. I don't want things just staying there at the spot where I applied the sample. So movement is going to be a positive thing. I want to see that. So 0 means it did not move. 0.1 means it barely moved. 0.2, okay, it's moved a little bit further away. We can kind of say, yeah, separation from the origin. We're okay with that. Not a problem. It cannot be 1. The reason it can't be 1 is because that means the spot distance has to perfectly match the mobile phase distance. And if the mobile phase went all the way up here to the top and my spot went all the way up to the top, well, okay, separation really didn't happen. Things just migrated with the mobile phase. It liked the mobile phase so well, and I hated the mobile phase or the stationary phase so much that it just traveled with the mobile phase and up and away it went. I don't really like when that happens either. You know, I want some resistance. I want some retention that's going to happen with these sample components. So I should not be getting RFs of 1. And I cannot get any RFs that are greater than 1 because that means the spot went further than this developing solvent. In no way does that ever make sense. That can't be a thing. So with these, 0.8 is a pretty good number. So 0.8 means it goes toward the top, and then anything in between this looks like a pretty good development. We feel comfortable with that. I'm going to say, you know, like 2/3, folks. 2/3 is like 0.66. It needs to go further than 2/3 up the plate. If I talk about 75%, 75% of the plate, that's 3/4. So if spots go further than 3/4 up the plate, then that could be an issue. And you're running the chance of having RFs greater than 0.8, because 0.8 is like 80% there. That's kind of what that number represents, right? If you multiply that by 100, that would be 80%. So as you develop, look where the developing solvent has made it, the mobile phase has made it, and then take 3/4 of that height. Spots 3/4 and below, great. If spots are greater than 3/4 and it's nestled near that mobile phase developing line, you could have an issue. You need to adjust the mobile phase or adjust the stationary phase, something along with the method to get those RFs in the ideal value of 0.2 to 0.8. Next up, since we're talking about migration, let's talk about 2D migration. What on earth is 2D migration? So 2D migration is the idea that we can do a two-stepper. All right, so you ever like line dance or square dance? Two-steppers. Oh, yeah, okay, yeah, I'm going to do two-step. All right, so the two-step or 2D plate development works like this. Up here at the top, you see A, B, and C. And then here you see X. All right, so X is actually the sample. That is an unknown. This is what my sample is. I'm trying to figure out what's there. And then A, B, and C, these are all standards. There are things that I know. There are things that I've applied. We're going to see if something matches up to them, yes or no. All right, so the plate's going to go in and development is going to happen. So up it goes. Not a big deal. Normal kind of process. Nothing special. Notice, though, what I did. I put the standards like way over here on one side, and then I put a sample over here in the corner on the other side. I kind of left the middle empty for a reason. I'll talk about that in just a second. But the position of these, very important. All right, so during that first development, what happens is that things move. So as you can see, the A spot traveled up and we get a new spot location. The B traveled up and the C traveled up. Not a big deal. I've got my mobile phase line up here. And then with that mobile phase line, that's great. That's not an issue. That's not a big problem. That's normal. I can calculate RFs on here all day long. And it looks like X is going to match up with the component A. And I'm going to look at this and I'm going to say, oh, well, that means component A has got to be part of the sample. Yeah, you're going to fall for a trick, though, because you're assuming that only one spot should be in X. X, that unknown sample, could have more stuff in it. And maybe the first development like this is not appropriate. Maybe that very first development is an issue that we need to take control of. I need to make it better. So what would happen here is that I would take the plate out and I would dry this just like normal, completely dry, get rid of that mobile phase. Separation doesn't take place anymore. I take some measurements. I circled some spots, blah, blah, blah. And then what's going to happen is that I'm going to turn it. I'm going to rotate it 90 degrees. So this is going to be my new starting edge that is now down here, right? I turned it 90 degrees. I rotated it. Notice where my X is at. My X, which is my sample, is still right there. Not a big deal. It's still there. It's not moved. I've not affected it in any form or fashion. But maybe this time I know that that X is a little more complicated than what I thought it was originally. So what happens here is that I could actually change the mobile phase, and I could do it drastically. Doesn't matter. Because this is going to give me a new start line. Maybe the first mobile phase was okay. It made things move, but it didn't really kind of affect the closeness of what some of these compounds might have together in a relationship. Some of them are really tight family members. So it's going to be harder to separate them a little bit more. So I turn it after the first round of separation. Maybe I'll choose a different mobile phase after the first round of separation. That's fine. And then over here to the right-hand side, notice what's happened. I get another A, B, and C start period. So those are, again, standards that I'm applying onto that plate. And with the second round, I'm like, okay, here we go. We're going to develop. And then it's going to do the same as what it did before. Whoop, up, up, and away. Then I'm going to stop it. When I stop it, look at what happened to X. X was right here. In that second mobile phase, it actually did separate into two components. Absolutely it did. That was not expected. First round only showed me one spot. But this was the misconception that I told you very early on. Just because you see one spot does not mean that it is a clean standard or a clean sample. There could be other impurities that are there. It just traveled along for the ride. You need to kick it out at some point in time. And this is where our chance of kicking it out of the car. Nope. No more free rides for you. Pay up for your next Uber. I'm kicking you out. You got to figure out something else to do. But we get 2 spots here with this sample that we thought was pure. Notice A, B, and C. So the A matches up again quite well. Here is B, and there is C. So that second elution and that second solvent has let us know absolutely this is A. This is A. It matched it in the first round and it matched it in the second round. But the problem here is that in this second round, I get a spot and it looks like it matches B. But folks, look, that B is dark and this spot is not dark. They did that for a reason. So they're letting you know this is not B. If it was B, you would have seen B separate out in the first round. A and B separated easily. Look at this. There was A and there was B. They separated, so it did not separate here with X. That was not part of it. So that means B is not there. A is there because A matched in the first round, absolutely. When we turned this 90 degrees, then, we were just like, okay, well, let's apply the same A, B, and C here, or let's do something different here. It does not matter. But if this was A, and if that came from the first round, then it should still match A, and we do see a match. It's right there. So yes, A has been confirmed. Absolutely. It matches A in the first round. It matches A in the second round. That is not a surprise, surprise. What is a surprise, though, is that other little piece that have separated. It looks like it's close to B, but they drew it. They didn't darken it in. So that's their way of letting us know it's a different color. It's slightly a little bit higher in RF, so it's close, but folks, it's not an exact match. It is not B, and it's not C. Nowhere near C. This is 2D TLC development. That's what this is. So the rule of thumb here with 2D TLC is to develop it, turn it, and develop it again. This is great for very complex samples that have a lot of components in it that you want to separate maybe a little bit better. That is what this is all about. One round of a mobile phase in one direction might not be good enough. You might need that 2D arrangement to take place here. Notice what happened in the diagram. If you look at the 2 mobile phases are often used, the very first bullet point, place the sample and standards in opposite corners. That way, when you do turn it, you don't interfere with everything. Remove it. Make sure you dry it. Put it back in with a 90-degree turn and do a second development all over again. Here's another example of 2D TLC. These are just lipids. Lipids, aka fats, that are extracted in some form or fashion, maybe from your skin, maybe from something else. So the first direction looks like it went up. So as we can kind of tell, look at, okay, we go up, we go up, we go up, we go up. The second direction, once we turned it, went that way. So spots began to separate from each other, maybe. And again, a very complicated mix of a family of compounds that have very similar structures that we need to separate from each other. So we need to do 2 rounds of development. Mobile phase number 1, if you look at this, it's chloroform, methanol, and water. Mobile phase number 2 is chloroform, methanol, and water, but they add a little bit of acetic acid in here. Not much. That acetic acid is going to be a ratio of 13. So they do change the mobile phase slightly, but nothing drastic, nothing major. You don't have to do it drastically. You could. But here was just a little bit of an acid and just a little bit of a ratio adjustment. And folks, we get separation again. From what we thought were clean spots in the very beginning, well, they weren't necessarily clean spots anymore. They were different. 2D TLC. Next, we talked about this already. TLC can be a precursor for HPLC. Very often, we like to do TLC first, And if we do it first, it gives us an idea of what's going to work and what's not going to work. Then that can transfer over into an HPLC method. Absolutely, it can. There's not an issue with that. It can do this. Not a problem at all. There's the TLC plate. I see some separation on it. I see spot number 1, and I see spot number 2, and I see spot number 3. But the way that this equates to HPTLC is a little different. All right, so let me explain. These spots toward the bottom, they're moving slower. So what's happening here is that this spot, it's moving faster. It has went faster up the plate. Its migration rate is much quicker. It has a higher RF value. If I allowed this plate to continue to develop, this spot, whatever component that is, and it goes right off the edge. The world's flat. It goes right off the edge. Well, if this was a column and not a plate, what this would mean is that the one that's moving faster is going to run through the column quicker. If it runs through the column quicker, it leaves the column quicker. So what's happening here is that on HPLC that actually uses a column, these components are going to be injected. And when those components are injected, separation is going to start taking place. One of these components is running much, much faster to get to the other end of that plate and to the other end of that column. So that one that has a higher RF, guess what, folks? That is the very first one that comes off in a chromatogram of a typical HPLC method. The second one that's moving a little bit slower, it's going to take a little bit more time for it to go off the plate. Therefore, it means it takes a little bit more time for it to come off the column. And if it takes a little more time to come off the column, then it's going to be kind of the middle one. It's got a lower RF. And then the one with the lowest RF down here at the bottom that's barely moving. It's like moving like a tortoise. It's barely moving, barely creeping. It's going to take its time. Up, 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 up. It's going to go. And finally, it reaches the edge of the plate. Okay, well, the same thing's going to happen in the column. It's going to go off to the edge of the plate. When it goes off to the edge of the plate, it goes off to the edge of the column, and it finally comes out. And our HPLC machines will see it. Well, that is why this is often the furthest for retention time. It's all about retention time, folks. So this retention time of that peak, that means that if this was on a plate, this would have the lowest retention factor, RF number. The one that is the fastest, that retention time, it zoomed through that column. It came out the other end very quickly. Okay. Well, what that means is that as it travels up the plate, if I calculate a RF, this is going to have the highest RF value because it's traveling the fastest. That is how TLC relates to HPLC. Great way for a precursor, great way to test a method. It gives me an idea if things are going to separate. It also gives me the idea of the order in which they do separate. I'll know which peak is going to come off first, which peak is going to come off second, which peak is going to come off third. The peak that comes off first in HPLC is going to be the highest one on a TLC plate, and then the second one, and then the third one. All right. What you see here again are compounds in the middle. Compounds, I can actually kind of talk about polarity here for a bit if I wanted. The majority of the structures here in the middle are very similar. You know, I see like 3 rings. They're not benzene rings, by the way. They don't have any double bond delocalization in them. But I see 3 6-membered rings and a 5-membered ring on all of them. So this one and that and that and that are all the same. I see a double bond in every one of those too. So none of those are going to really be different in that kind of scenario. I see a double bond over here to the left-hand side bottom. All of those have that double bond there. That's going to be basically a ketone type of functional group. So that's not making it any difference. The only thing that's making it a little different is these groups that are attached to the ring. So look at this. There is an OH group there. There's an OH group here that makes that a little different. There's a C double bond O group that's going to be up here. There's another OH group that's going to be there. Folks, those are very polar functional groups. Those polar functional groups are going to be interacting with the stationary phase, but they also interact with the mobile phase as well. So let's see what the mobile phase is. Our mobile phase is methanol and water, and it is a 70-30 mix. This is a very polar mobile phase here. Let's take a look at our stationary phase. What did they decide to use? Not the typical silica with an OH group. They chose to use a C18. So that means it's silica that's been modified with 18 carbon chains. That is a very non-polar type of stationary phase. So that hydrocortisone, which is what structure number 3 is, that has all of these polar groups on them, is going to be interacting with the polar mobile phase, and it's not going to stay around for that non-polar stationary phase. It just doesn't get along with it. So it's going to interact with the mobile phase more, it travels with the mobile phase more, and then sooner or later, it's going to go off the plate, and it's doing it quicker because of the structure that it's bringing to the table. Go figure. I was able to explain why this happens, and all because I know the basics of how TLC actually operates, right? That's all that this is about. Stationary phase, mobile phase, polarity, electronegativity values. That is what made these judgment calls. I was able to predict it before it even happened. Okay, well, if you take a look at number 1, well, that structure is pretty much the same. There's no OH groups on them at all, not one. And then, if anything, it's got this C double bond O up here at the very top. Well, so did structure number 3. Nothing about that is special. Nothing about that brings any polarity to the table. Therefore, it's not going to interact with that methanol and water that is superpolar. It's going to stay with the stationary phase a little bit longer because it gets along with it better. So therefore, it barely moves through the stationary phase. And in other words, if I injected this on an HPLC system that had a C18 column that used 70-30 methanol water, then it's going to take forever for it to come out of that column. And that's because, and that's why it has a longer T sub R. A longer retention time is needed because it takes longer for it to come out the column because it's interacting with the stationary phase even more. All right, so we've got maybe 1 or 2 videos left. I'm going to say maybe 1. I can cram it all into 1. So with that next video, we'll come back and we'll talk about more details. I'll see you then.